Welcome back to Calculus for Economics, everyone. This is my video for you on Monday, March 23rd. So it's our first day back from spring break, our extended spring break that was, extended or disrupted, however you want to look at it, due to the COVID-19 virus. I certainly hope you all are healthy and safe and practicing social distancing and good hand washing and all those things. I wanted to use this video to update you on what I'm thinking about in terms of our class policy and also to take us a little bit further into just the calculus. First of all, we were planning a test our first week back from break covering the material that we had done since test one, stuff on revenue, profit, elasticity, some applications of calculus. Well, that's canceled. We're going to, it's not like we're leaving that material behind, and I will be assessing you on that material in a couple of different ways, which I'll explain as we go forward. But as far as just in-class tests for the rest of the semester, we're not going to have any. All our assignments are going to be done online. Now, I am planning some online quizzes that will be different in format than the WebAssign homework that you're already used to. But they'll still be delivered through WebAssign. The main difference between them and the homework is that they'll be timed and you'll only have one attempt per problem on the online quizzes. So I'm going to put an example online quiz up there for you this week. In fact, it should be up there by the time you see this video. And we'll talk about those in a subsequent video. If you look at the assignments that are actually on WebAssign already, you see that there's one, homework 28, on the second derivative test. This is actually, it was assigned before we left for break. And so I've extended it, of course, and made it due Monday, that's today, at 11 p.m. And I also sent you out a link to a video in which I basically kind of reviewed that material and explained a little bit about how to use the second derivative information to get information about a function. So that video ought to help you make your way through homework 28. There's also another homework that's due Wednesday. That's homework 29, and that's on applied optimization. And so that's what I'd like to talk to you about today. I'm going to go through a short example in which we apply some of these calculus problems or concepts to a problem in optimization. And that, along with a video I'll post on Tuesday, should help you make your way through homework 29. So let's go ahead and get started. I want to actually use the ebook here. There's a nice example, and we're in section 4.5 of our text right now. Their very first example gives a lot of the essential components of the kind of optimization problem we'll be looking at. In this example, it's a real simple one. A man wishes to fence a rectangular garden, and he has 50 feet of fencing which he wants to use to enclose the garden. So what would be the dimensions of the rectangular garden that would enclose the largest area? So, you know, he could fence in any kind of rectangle, from a square to a long, thin rectangle to a short, fat one. But what rectangle could he use that would maximize the area of the garden? That's the problem I want to address today. So let's jump right into it. Here, I've just sort of written down the basics of the problem and drawn myself a little figure. So we're given that we want to make a rectangular garden, and we're given that the total amount of fencing we have is 50 feet, and we want to find the garden that maximizes the area. So a way to get started on a problem like this is to think about the variables that are involved, give them names, and then start relating the variables to each other and to the ultimate goal. And our ultimate goal here, of course, is to maximize the area that we enclose in this 50-foot perimeter garden. So obviously area is one of the variables that we'll be interested in. In fact, it's sort of the main one, right? So I'll just call it A, and that's the area of the fenced-in garden. We're going to try to make that as large as possible, but what do we have to work with in order to get an area? Well, we have the 50 feet of fencing, and that 50 feet has to be distributed in this rectangle. So we got to use the 50 feet to go around this rectangular perimeter here. So one idea would be to think about the amount of fencing you're going to use on the sides, and so that would be an X, that would be that length here for that side, and of course the opposite side would have the same length, so that would be another X, and then a length for the front and back of the garden, so I'm going to call that Y. And of course the front and the back would have the same length as well. So let's use those two variables. X is the length for the sides, and Y is the length for the front and the back. So how can we use these variables to help sort of find our way through this problem? Well, one thing we can try to do is express what's given and what we're trying to find in terms of these variables. So for instance, we're given that the total length of the fencing is 50 feet, right? And so that would tell us that this entire perimeter has to be 50 feet in length. But the perimeter consists of these two sides, each of which has length X, and the front and the back, each of which has length Y. So that would say that the total perimeter, which is 50 feet, would have to be 2X plus 2Y. That makes sense, right? Because we're using 50 feet to fence in the garden. So that's one piece of information that we've sort of translated into mathematical terms. Often this piece of the problem is often called a constraint for the problem. It's a constraint because no matter how we do things, we're still going to be using 50 feet for the whole garden, 50 feet of fencing. So that's kind of a given. We've got to use that 50 feet, and that equation will be true no matter how we decide ultimately to shape the garden. So that's called a constraint of the problem. The other variable that we're interested in is area. And of course this is a rectangle, so we can relate that variable to the other two variables. Area of a rectangle is just the product of the side lengths. So A equals X times Y relates the variable I really want to aim towards here, which is the area, I want to maximize that, to those two side lengths X and Y. Now, what we want to do is maximize the area. That's our objective. So a lot of times this piece is called the objective function of the problem because we want to, it's our objective to maximize A. So we want to maximize A here. And so with that, we've translated the problem into mathematical terms. And now the question is, what do we do in order to solve the problem? Well, let's just keep plowing ahead with this. I've just basically copied some of that information onto this second slide here. And we know that the area is, of course, x times y, and you have your constraint down here. We know how to maximize and minimize functions. We've talked about that and with respect to the first derivative test and the second derivative test. So why don't we just apply that information to this function? We want to maximize the area, right? Well, the problem is this function is actually a function of two variables, x and y. And the calculus that we've done so far is all about functions of a single variable. We've only talked about, maximum, like, f of x equals x squared plus 3x. How do you find the maximum or minimum of that? We've got a function of two variables, so how can we sort of apply those techniques here? Well, the answer lies in sort of putting together the constraint and the objective function. The constraint, you'll notice, is an actual equation involving x and y. Now, what I'd really like is for my objective function, the area, to be a function of x alone. Well, what if I use the constraint to solve for y in terms of x? Right? So let's solve for y in the constraint. You would get 2y equals 50 minus 2x. And so y would be 25 minus x. Knowing that, I could go ahead and say that my area function is x times y, but y is 25 minus x, so I would have that. And now that area function is a function of x alone, and I could at least use, or try to use, the calculus that I know for functions of x to find its maximum or minimum. So that is a good thing. One thing we might want to do here is go ahead and multiply this guy out just because of what we're going to be doing later. So let me go ahead and do that. That's 25x minus x squared. So now our problem is to maximize the function a, which is 25x minus x squared. Now, we have techniques for doing this, the first derivative test, the second derivative test. But this is an applied problem. The variables mean something, right? A means area. X, for instance, means the side length of our rectangle. When you have an applied problem, sometimes values that make sense in sort of a pure mathematical setting don't make sense in the applied setting, right? So, for instance, here, just if I were giving you this function as a mathematical function, it would make perfect sense to plug in x equals -1 and find out what a was. But in the context of the applied problem, that doesn't make sense, right? Because x is a length. It's the length of this side of the rectangle here. So negative values of x don't matter for us. In other words, there's a domain of interest here in the applied setting that we need to be aware of. And that would be that, first of all, that x actually has to be bigger than 0, right? But actually, we can say a little bit more than that, because by the same token, y has to be 0. I mean, bigger than 0. And if you look down at this equation, y is 25 minus x, that's all good as long as x is less than 25, right? If x is bigger than 25, y is less than 0. And that doesn't make sense from an applied perspective. So we also have to have x less than 25 here. Okay, so now we can restate the problem purely, in mathematical terms, but tied to the practical realities that the problem imposes. So we want to maximize a equal 25x minus x squared for values of x that run between 0 and 25. And so that's our new problem. And now we've got basically everything we need in order to solve the problem. So let's see how we would do that. And this now is going to go back to our first and second derivative tests. So here I've just written the problem over what we've discovered so far. And how would we do it? Well, remember, we need to find critical points first. The critical points of a function are the places where the derivative of the function is equal to 0 or undefined. So we need to look at the derivative of a prime. That's just 25 minus 2x. So the critical points are the places where this guy is equal to 0, because there's never undefined. And you get 2x equal 25, or x equals 25 over 2, which is 12.5. So that's our critical point. So remember that critical points are candidate maxes or mins. Now, so we need to figure out whether this critical point is a maximum or a minimum, or possibly neither. And so the go-to method for doing that is the second derivative test. So is it a max or a min? Let's try the second derivative test. So there, basically the idea of the second derivative test is to look at the concavity at the critical point and then draw a conclusion. So we need the second derivative, a double prime here. Well, that's just going to be the derivative of a prime, but that's just negative 2, which is less than 0. So think about it now. You've got a critical point, 12.5, where the derivative is 0. So that means you've got a flat tangent line. And then you know that the second derivative is negative. So that means you're concave down, right? So remember back before the break, concave down and flat tangent line. You've got to be at a maximum, right? And so the second derivative test tells us that x equal 12.5 provides well, and let me pause here. I was about to say relative maximum, and that's true. I'll just go ahead and write that. But it's also an absolute maximum, because think about it. This guy is always concave down. The second derivative of our area function is always concave down. And so the function, if it has a maximum, that has to be the absolute maximum of the function. And so we could actually say that in this case, because the function is always concave down, this is not only a relative maximum, it's the absolute maximum. And in a lot of cases in practical problems, you are interested in not just whether a point provides a relative maximum, but actually whether it provides the absolute maximum or not. And so we have that information here. So the dimensions of the fence that gives us the largest area, so the dimensions of the largest possible rectangle in terms of area are x equal 12.5. And then for the y, you'd want to go back to our previous work. And here we found that y was always going to be 25 minus x in this situation. So y here would be 25 minus our x value, 12.5, and that turns out to be 12.5. And then finally, we could think, well, how big? How much area do you get? Well, the area of the maximizing rectangle would just be x times y, right? And that would be 12.5 squared. So that's going to be 156.25, I believe, if I did that right. So yeah, there we have it. Notice, by the way, that because x and y are equal, the rectangle that gives you the largest area turns out to be a square, which may not be that surprising. Okay, so there we have it. I hope that is helpful. We're going to have another video shortly about another optimization problem. And then I think you should be ready for homework 29, which again is due Wednesday at 11 p.m. So stay tuned for that. In the meantime, stay healthy, and I will talk to you again soon.